Hello students, welcome back to SapphireBlueChemspark. Today let us start our session, the chapter Coordination Compounds from Inorganic Chemistry. What are called coordination compounds? These are a special type of salt in which the central atom or ion are surrounded by a cluster of ions or molecules. Such compounds are said to be coordination compounds. What type of elements can able to form coordination compounds? This is we already discussed in our D and F block elements. The transition elements, they have a tendency to form complex formation. This is why, because they have a very small size, high charge density, and they have n-1d and ns vacant orbital. So these vacant orbital can accept a pair of electron donated by these ions or molecules, and hence the D block element, especially the transition elements, are capable of forming coordination compounds. What is the need of learning this chapter? Because these chapters, it finds its application in animals, in plants, as well as in minerals also. So when we say about in plants, this is observed in the form of chlorophyll. It is a complex of magnesium metal. Magnesium porphyrin complex is said to be the chlorophyll. The chlorophyll is nothing but the greening matter of the plants. And also in animals, it is present as a form of hemoglobin. Hemoglobin is a complex of iron porphyrin complex. So here the chlorophyll is mainly used for its photosynthesis process, and in this case the hemoglobin, where the heme is responsible for the carrying of oxygen or even the carbon dioxide. That means the transportation of blood. So during the transportation of blood, oxygen is being delivered to all part of the cells, from where the carbon dioxide is being taken away. So that is what being done by the hemoglobin, a complex of iron and porphyrin. Also it is observed in vitamin B12. Vitamin B12 is also known as cyanocobalamin. This is a complex of cobalt metal. And these coordination compounds, they are finding their applications in most of the field. For example, when we say extraction of metals like noble metals of gold and silver, here those metals being extracted by the formation of cyanide complex, from which the metals will be recovered. And these compounds also be used as medicine in the treatment of cancer. That example is cisplatin. And these are also used in industrial way also. In the industrial processes, it is useful for the determination of hardness of water. Hardness of water is due to the presence of sulfate or chlorides of magnesium or calcium salts. So the amount of hardness present in water can be estimated using such compound. Here EDTA will be applied. And also it is useful in electroplating process. Electroplating, a less valuable material can be converted into more valuable material. For example, a silver metal can be converted into gold plated metal. So such processes and all, the complex compound is being employed. So this is because of their unique behavior, as well as they do not form any coarse formation during the electroplating. If at all in the form of complex compound, that gives even deposition over the electroplating. So because of their unique nature and behavior, we have to learn about coordination compounds. And this chapter, it deals about the different terms which are used to explain about the coordination compound, called terminology we will learn. And the different theories that explains about the nature of bonding between the central metal atom or ion with the ions or molecules also be studied. And we can have the different types of isomerism exhibited by coordination compounds also we are going to explain. Besides that, we have some carbonyl compounds and their applications. So all those topics will be covered in this chapter. The next one, addition compounds are molecular compounds. Addition compounds also known as molecular compounds. How these compounds are prepared? These compounds are prepared by taking two stable simple salts. Simple salts are composed of only one cation and only one anion. Such salts are said to be simple salts. So in this we may find potassium sulfate. It is made up of potassium ion and the sulfate ion alone. Such salts are said to be simple salts. So when we have two simple salts in their stable form, when we mix their aqueous solution, it gives rise to the compound of the type. For example, potassium sulfate with the aluminium sulfate, but the combination of these salts must be in their stoichiometric proportion. The proportion is very important. So when these compounds are taken in their stoichiometric proportion, we will get potash alum. So potash alum is prepared by mixing potassium sulfate and aluminium sulfate in their stoichiometric combination that gives potash alum. Or else, if we have ammonium sulfate with the ferrous sulfate in their stoichiometric proportion, we will get more salt. So other case, if we have copper sulfate with the excess of ammonia, I am getting the compound of the type CuSO4.4NH3. These compounds are formed by taking their stoichiometric proportion upon boiling, and on cooling a crystalline appearance of the salts will be formed. Such crystalline substances are called molecular compound or addition compound. So why do we keep dot between them? Because they just mixed. That's what the two salts I have taken, they mix to form their solution, in which I am identifying what are the compounds formed. How do they differentiate, or how do we find any difference of these two types of salts? So when these salts are taken in water, we may get the different kinds of ions present in the solution. How we can find potassium sulfate, aluminium sulfate in water? It gives rise to K plus ion, Al3 plus ion and SO4 2 minus sulfate ion. Or else if I take more salt in water, I am getting ferrous ion, ammonium ion and sulfate ion. At the same time, when I take these two compounds in water, I am getting the ions of the type CuNH3 4 plus ion, 4 2 plus and sulfate 2 minus ion. Or this compound, it forms the compound of the type, it forms the ions of the type FeCN6 4 minus and K plus. How do we analyze the formation of such ions in their solution? That can be done by taking simple experiments for their presence. If I conduct simple experiments for the presence of potassium, aluminium and sulfate, they do answer for their presence by giving positive results. Similarly, these more salt also able to answer for the presence of ferrous ion, ammonium ion, sulfate ion. We have simple experiments, that is what doing in our salt analysis or the qualitative analysis, based on which only we are identifying what are the ions present in the aqueous solution of such addition compounds in water. At the same time, when these compounds are taken in water, they do answer for the presence of sulfate ion as well as for the presence of potassium ion. But there is no positive answer for the presence of copper or even for the presence of iron. This is what that makes a major difference between the two types of addition compound or the molecular compounds. So the first case in which all the constituent ions are produced in water are said to be double salt. So these are simply known as double salt. And here we are getting the ions, but one of the ion is simple ion, but in the other case they form a complex ion in which the metal is not free. Such compounds are said to be complex compounds, or we can say coordination compounds. So this is what the major difference between the formation of the two compounds, two salts of the type addition compounds are molecular compounds. Okay, in these complex compounds where the metal is surrounded by a cluster of groups or ions or molecules is said to be what I told you, coordination compounds. And these compounds, they do possess a dative bond or a coordinate bond between the group of cluster of groups with the central atom. How that dative bond is formed? Because in such cases the electrons required for the formation of a chemical bond is given by only one of the group, not by both. So there is no mutual sharing of electron. The bond is formed by giving away a pair of electron by only one of the group to the other one. That's why they do possess either a dative bond or it is known as coordinate bond. So we can conclude addition or molecular compounds able to form either a double salt or a complex salt. Double salts in which the metal ions are free, and in complex salts metal ions are not free. Double salts, they do give their positive test for their presence, but complex salts, they do not give their positive test for the presence of metal. So this is how we can explain metal ions are not free in the complex salt, but metal ions free in their double salts. That's all. The formation of addition or molecular compounds. So in this unit we are going to discuss about the coordination compounds. So the branch of chemistry that deals about only the coordination compounds is known as coordination chemistry. So the first thing to explain, to know more about the coordination compounds, already we prepared the molecular or addition compounds, and we discussed also the two types of double salts which are formed upon the combination of two simple salts. One is a complex salt, the other one is the double salt. So to know more about the formation of complex ion, we are going to discuss about WERNER theory of coordination compounds. This is the first theory proposed by Alfred WERNER. So he is also known as father of coordination chemistry. So let us find the formation of cobalt 3 chloride ammonia complexes. By knowing these complexes, we can explain about WERNER theory. Cobalt 3 chloride, so here the oxidation number of cobalt is +3. When cobalt 3 chloride is mixed with ammonia, we are getting a different colored complexes. So the first one, I get yellow colored complexes where the formula is COCl3 6NH3. And in other case, I am getting a rose, or we can say even like pink color. So where the formula is COCl3 5NH3 with the water. Or the purple colored complex where ammonia, so from yellow to the blue green, you may find the difference in number of ammonia that is combined with cobalt 3 chloride. So first case, cobalt 3 chloride combines with 6 moles of ammonia. Second case, cobalt 3 chloride combines with 5 moles of ammonia and 1 mole of water. In the third case, it has 1 mole of cobalt 3 chloride with 5 moles of ammonia. And with the next case, it can have 4 moles of ammonia with the cobalt 3 chloride or 3 moles of ammonia with the cobalt 3 chloride. So when we move from the first complex to the last complex, we may find there is difference in number of ammonia molecules that make complexes with cobalt 3 chloride. So when these number of ammonia molecule present in the complexes differ, color of the complexes also differ. So we can identify what would be the complex of the type by the mixing of these two. We can have hexaamine cobalt 3 chloride. So its color, it is said to be yellow in color. And the next one, it has CONH3 5H2O. So in addition, in place of one of the ammonia molecule, a water is introduced. So the presence of water that makes its different color, that becomes a pink color or rose color. And in the next case, where instead of water, one of the chlorine enters into the complex, where 5 times of ammonia and 1 time of chlorine is there, so that makes its complex color becomes purple. Or in place of 2 molecules of ammonia, if 2 chlorine ions are replaced, then the color it goes to one as green color and the other as violet color. But the proportion of ammonia and chlorine in the complexes are similar, even though they are differing in their colors. This is because of its isomeric nature. And the last case, there are 3 times of ammonia with the 3 times of chlorine, that makes the color of the complex as blue-green. Okay. How did you analyze the presence of chlorine outer the complexes, whether it is 3 or 2 or 1 or 0? That can be done by treating these complexes with silver nitrate. Silver nitrate is AgNO3. Why this compound is taken? Because silver nitrate only can give a curdy white precipitate of silver chloride upon reaction with the chloride ion. So we can analyze these complexes by treating with the silver nitrate. How many moles of silver chlorides are formed? Suppose if silver nitrate is treated with this complex, I am getting 3 moles of AgCl, because the outer ion it has 3 times. Already we discussed the outer ions are simple ions. So this is what the complex ion. How many simple ions I have? I can write this is as 3Cl minus. So these 3Cl minus can combine with the 3 times of silver nitrate. So it forms 3 times of silver chloride. So I can write the complex proportion of the type is the complex ion 1 time present, the simple ion 3 times present. So the ratio of the complex to simple ion is 1:3. Similarly, when this complex is treated with the chloride, once again I am getting 3 times of AgCl because of the presence of 3 simple chloride ion. So therefore, once again its simple complex to simple ratio is 1:3. But when I go here, the simple ion is only 2 times chloride ion there. So it dissociates, it can give rise to 2Cl minus, that makes 2 times of 2 moles of silver chloride is formed, and hence this ratio it becomes 1:2. The other 2 cases, we have chloride ion only 1 time present as simple ion. That's why here they do able to form 1:1 complex, 1:1 complex, because of the chloride ion present singly. But in the last case, there is no simple ion, so no silver precipitate, no curdy white precipitate is formed. So no curdy white precipitate. So we can formulate a variety of complexes just by treating cobalt 3 chloride with ammonia. So the different variety of formation of complexes can be observed by their different color. So based on this, we are going to explain about WERNER's theory. So according to WERNER theory, a complex is made up of 2 valencies. One is said to be primary valency, the other one is said to be secondary valency. So this is primary and this is secondary. What do you mean by primary valency? Primary valency is nothing but the coordination complexes, the metal it is exists in its particular oxidation state. That oxidation state of metal ion is said to be primary valency. So primary valency corresponds to the oxidation number of central metal ion. Suppose the central metal atom may also be present. When it is in its atom, then the primary valency becomes 0. If at all it loses the electron, that becomes the positively charged ion. When it doesn't lose any of the electron, then the atom in its zero oxidation state. But in this complex, I had taken cobalt 3 chloride only. So oxidation state of cobalt is 3. That's why the central metal ion whose oxidation state is said to be primary valency. And how this primary valency is satisfied? Because if we have the cation, that must have the anionic part, then only the salt will be neutral. So when this metal ion, it has a positive oxidation state, then definitely those positive oxidation state will be neutralized by its negative ion. So the primary valencies are satisfied by only the negative ions. So in this case, what are those negative ions? The chlorides are negative ions that balances the positive charges of these complexes. The next point, what about secondary valency? Secondary valencies are actually a fixed number of central metal atom or the ion. Let us discuss about these complexes. You may find within the complex the number of ammonia molecule inside the complex is 6. And in the other case, ammonia 5 times, water 1 time, that is equal to 6. The next case, ammonia 5 times, chlorine 1 time, 5 plus 1, 6. Next case also 4 plus 2, 6, 4 plus 2, 6. Here 3 plus 3, 6. See, in all these complexes, cobalt, it has a fixed number of a particular value, that is called secondary valency. That secondary valency is actually known as coordination number of central metal atom or the ion. It is always fixed for the particular complex. So here we can say the secondary valency that corresponds to coordination number of central metal ion, and it is satisfied by what kind of molecule that can satisfy? Either the neutral molecule. What kind of molecules that can satisfy the secondary valency? The first case we said primary valency is always satisfied by negative ions, but the secondary valency that can be satisfied by either neutral molecules or by the negative ions, or we can say even the positive ions. So the secondary valencies are always a fixed number of central metal atom or the ion, and whose values are always satisfied by neutral molecules, negative ions or positive ions. In these cases, here ammonia is a neutral molecule, but chloride is the negative ion. So secondary valency of cobalt is satisfied by both the neutral as well as anion for this secondary valency or its coordination number. So the fixed number of these groups which are enclosed in a square bracket is said to be coordination number of central metal atom or the ion. So in all these cases, coordination number of cobalt is 6 only. The next one, the primary valencies are non-directional in nature, because it is the group which are just satisfying its positive valency only, and it does not go in any direction. Which of the direction it has to be oriented, it has no rule at all. But the secondary valencies are directional in nature. These secondary valencies that has to be oriented in a definite direction given space. So the projection of secondary valencies at a particular direction in a given space that gives rise to the geometry of the complexes. Those geometry of the complexes usually explained in terms of polyhedra. Here I said the coordination number of cobalt is 6. That is 6, it corresponds to the geometry of the complex as octahedral manner. such a way if at all 4 is there, that can be given by either square planar or tetrahedral. So depends on the coordination number, we can even arrive the geometry of the complexes based on their projection to the definite direction in a space. So secondary valencies are directional in nature, but primary valencies are non-directional in nature. Okay. So according to WERNER theory, we have primary valency and secondary valency. Those two valencies that can be represented in the form of a sphere. So in this we have two spheres, one is inner sphere, the other one is outer sphere. This is what the central metal atom or the ion. It can have even a positive or positive charge. That must be in a positive charge, the charge that depends upon its oxidation number. And in this case only the positively charged metal is firmly attached with its secondary valencies, that is the group of molecules or the negatively charged ion or even the positive ions. So here the metal is firmly attached with its secondary valency, unable to leave the metal free from its complex. That's why this sphere is also known as non-ionizable sphere. So we can't able to get the free metal ion from this inner sphere. But the outer sphere is simply satisfied by the primary valency, and that could be ionizable. So we can say that is the ionizable one. So we said primary valency, secondary valency. Primary valencies are ionizable, secondary valencies are non-ionizable. That is also the another point that can be described from their structure. So we can give the octahedral structure of these complexes. So I have taken CONH3Cl3. So just like this sphere, we can represent the cobalt in which it is bonded with 6 ammonia molecule. So all those 6 ammonia molecules are represented in the octahedral manner of cobalt 6NH3, CONH3 6. And the 3 more chloride ion that is present outer the complex is given in its outer sphere. So we can represent, this is what the octahedral sphere of hexaamine cobalt 3 chloride. So we can say a coordination complexes will consist of 2 spheres, ionizable and non-ionizable spheres. Ionizable spheres are always the outer sphere, and the non-ionizable spheres are the inner sphere. So where the metal ion is not free because it is firmly attached with its respective coordination number, that means the secondary valencies. So we can conclude WERNER theory. WERNER theory, it has 2 valency, primary, secondary. Primary valency ionizable, secondary valency non-ionizable. Primary valency non-directional, secondary valency directional. Primary valency satisfied by only negative ion, secondary valency satisfied by negative ion, neutral molecule or even positive ions. And the secondary valencies are always a fixed number, and it is said to be coordination number of the central metal atom or the ion. That's all WERNER's theory. So let us close our today's session, and we will continue the same chapter in our following sessions. Until then, bye bye.